So in this video, we are going to start to apply the enthalpy or the energy of a reaction to an actual chemical reaction. So far, we've been calculating Q is equal to the mass times the specific heat times the change in temperature. Now we want to look at how much energy is in a chemical reaction. So if we take a look at these, there's a little introduction there that talks about, again, reviewing that if the flow of energy is a negative, then that indicates that it is exothermic, whereas if that flow of energy is positive, that indicates that energy is going in and it is endothermic. So we have three substances here. We have glucose, methane, and propane, and we can see their formulas, and then we see the enthalpy, the delta H, and it gives us a specific unit. The unit it gives us is kilojoules per mole. So what that actually means is that in this chemical reaction, for every mole, we are going to get that many kilojoules that are going to react. So we're going to write the balanced equation for the combustion of methane, the balanced equation for the combustion of glucose, and the balanced equation for the combustion of propane. So remember, combustion is the reactant plus oxygen. So our first one is going to be methane, CH4 plus O2. And then because this is a hydrocarbon and we are reacting with oxygen, combustion reactions with a hydrocarbon always end with carbon dioxide and water. So our products are going to be CO2 plus H2O. Our last step is going to be to balance it. So we're going to put a 2 in front of the oxygen. We are going to put a 2 in front of the H2O, and then we will be balanced. Now we need to put in the thermochemical information. So we can do this two ways. We can either put this at the end and put delta H equals negative 2,808 kilojoules per mole, or we can put that equation, we can put that number into the equation. So since it's negative, that means energy is exiting. That means energy is a product. So we would write this reaction CH4 plus 2O2, and that's going to produce CO2 plus 2H2O plus 2,808 kilojoules of energy. We don't have to put the negative on it because this is exothermic, and since we're putting the number directly into the balanced equation and we put the number on the product side, that automatically tells us that we are going to have this as a exothermic reaction, that is a product. So the negative is only involved when we have it at the end, with it being just being told to us that the enthalpy or the delta H of the reaction is 2,808 negative, tells us it's exothermic. Now we're going to do the same thing for glucose. Glucose is C6H12O6 plus O2, and then again our products are CO2 and H2O. We need to balance it, so we're going to put a 6 in front of the oxygen, we're going to put a 6 in front of the carbon dioxide, and we're going to put a 6 in front of the water. And then we're going to do the same thing. Our delta H for glucose is 2,808. Oh, I'm sorry, methane should have been 8,891. So ignore what I was saying. I did write it correctly, 891. So now the next one, glucose, is 2,808. That's a negative, and then we are going to rewrite the equation again, but we're going to put the actual number into the equation. Again, it's exothermic, so that means energy is a product, so we're going to put the 891 on the product side. So really, we can write these reactions two ways. So before I do propane, go ahead and pause the video, see if you can do it on your own, and then check and see if you did it correctly or not. So with propane here, again, making sure that you can write a combustion reaction. Products are going to be CO2 plus H2O. And then we do need to make sure that it is balanced. So we're going to go ahead and we're going to put a 5 in front of the oxygen, a 3 in front of the carbon dioxide, and a 4 in front of the H2O. Now we want to put in what our heat of our reaction is. And according to the chart, it's negative 2,219 kilojoules. The other way that we can write this is that we can have our materials and we can actually put in our energy into the chemical reaction. So since this chemical reaction has a negative, that means that we're going to put the energy as a product. So notice how I've got my energy of my, on the product side of my chemical reaction here. So this does tell me that there are 2,219 kilojoules of energy that are getting released every time I produce 4 moles of water and 3 moles of carbon dioxide, or when I have 1 mole of propane reacting with 5 moles of oxygen. That's how much energy is going to be released there. So you do want to make sure that you understand what this is really telling us. It's telling us that if I've got 1 mole of propane and I have 5 moles of oxygen, then that means I'm going to make this much energy. If I've got 3 moles of carbon dioxide, if I've got 4 moles of water being made, then that means this is how much energy is going to be released. So we're going to take a look at that on the next document. So this is where thermochemistry meets stoichiometry. So from the balanced chemical reaction, you can see that we've got methane, CH4, reacting with 2 moles of oxygen. And from that, we are going to produce carbon dioxide and water. 2 moles of water, 1 mole of carbon dioxide. And we've got a delta H. We have an enthalpy of our reaction. The enthalpy of the reaction says that we are going to release 890 kilojoules of energy. So we know this is exothermic. We know energy is a product. So the first question, letter A, says how many kilojoules of heat is released when 1 mole of CH4 is burned? Well, the balanced equation tells us how many moles are going to make how much energy. So if I look at CH4, I see there's no coefficient in front of it. So that means that for this balanced reaction, 1 mole of CH4 will produce that 890 kilojoules of energy. So the question says, how much heat is released when 1 mole of CH4 is burned? So that means I'm going to burn 1 mole, and that means that I am going to produce 890 kilojoules of energy. That's it. Now, letter B says, well, what if I burn 2 moles of CH4? Now remember, the balanced equation, there's no number in front of the CH4. So 1 mole is going to make 890 kilojoules of energy. So how much would 2 moles make? Well, we would multiply 2 times the 890 kilojoules for every 1 mole. That means that we would release 1,780 kilojoules of energy. Now letter C is where it does get a little bit tougher. Now instead of telling me how many moles, it's telling me how many grams were burned. But we know our stoichiometry. We know that we can take 13 grams and we can convert that to moles. How do we do that? We have to find the molar mass. How much does 1 mole of CH4 weigh? So I look on my periodic table. Carbon has a mass of 12.011. Hydrogen has a mass of 1.01. So I add 4 hydrogens and 1 carbon, which means the molar mass, 1 mole of CH4 weighs 16.05 grams. So if I have 13 grams, how many moles do I have? I'm going to have to take 13, divide it by 16.05. 1 mole is equal to 16.05 grams. So 13 times 1 mole over 16.05, I'm dividing. I'm going to find that I have 0.81 moles. Now remember, the balanced equation says 1 mole produces 890 kilojoules of energy, but we don't have a mole. We only have 0.81 moles. So that means we're going to use the relationship that 1 mole is going to produce 890 kilojoules of energy. We're going to start with what we're given of 0.81 moles, multiply by the relationship from the balanced equation, which then we solve and we find that we will produce 720 kilojoules of energy if we have 13 grams, because we don't have a whole mole, so we cannot produce 890 kilojoules of energy. Okay, so let's take a look at this next one. Again, remember the balanced chemical equation tells us how many moles. So this balanced equation says 1 mole of nitrogen and 1 mole of oxygen react, and they're going to produce 2 moles of nitrogen monoxide. And when we have that reaction going on, it says the enthalpy of the reaction is 180 kilojoules. Now, Notice this is positive. That is telling us that this is an endothermic reaction, that energy is going into this reaction. Energy is a reactant. Now, the first question says, how much energy is absorbed when 1 mole of nitrogen reacts? Well, remember the balanced equation tells us how many moles and how much energy. So since there's no coefficient in front of nitrogen, the balanced equation is telling us that 1 mole of nitrogen is going to require 180 kilojoules of energy. That's it. The next question gets a little more complicated. This time it says, well, how much energy is absorbed if I have 50 grams of nitrogen? So keep in mind that the balanced equation only tells us the mole relationship. So our first step is going to be, we're going to need to convert our 50 grams of nitrogen into moles. So we're going to use our periodic table, and we see that nitrogen has a molar mass of 14.01 grams, but this is N2. So that means that N2, 1 mole of N2 is going to weigh 28.02 grams. So we have 50 grams. We need to know how many moles that would be. So we use our relationship that 1 mole is equal to the molar mass, and we solve for how many moles we have. So if we take 50 grams and we divide it by 28.02, we find that we have 1.78 moles. So remember, the balanced equation says 1 mole gives us 180 kilojoules of energy. Well, we've got more than 1 mole. We have 1.78 moles. So we're going to use the relationship that 1 mole is producing 180 kilojoules, and we're going to use our 1.78 moles. And we solve and we find that if we've got 50 grams, because we've got 1.78 moles, we're going to make 320.4 kilojoules we're going to need to absorb that much energy. All right, so the next one, again, remember, the balanced equation tells us how many moles. So this literally says that 4 moles of iron react with 3 moles of oxygen and produce 2 moles of iron oxide. Our enthalpy of the reaction is negative, so again, remember that tells us this is exothermic, and that tells us that energy is a product, that energy is exiting the system and being released. So the first question says how much energy is released when 4 moles of iron react. So I'm going to look at iron in the balanced equation, and I see that it has a coefficient of 4 in front of us. So this balanced equation is actually telling me already that 4 moles of iron are going to produce 1,652 kilojoules of energy. That's it. Now, the next question, though, says, well, what if I only have 1 mole of iron? So here's what we're going to do for this. We're going to use the relationship that we know that 4 moles of iron produces 1,652 kilojoules of energy. We're going to use that and basically create a conversion factor that 4 moles produces that much energy. So we're going to start with how much we really have. We only have 1 mole of iron. We're going to multiply that 1 mole of iron by our conversion factor, our relationship that we know that 4 moles of iron produces 1,652 kilojoules. If you look at this, this shows that basically what we have to do is we have to take 1,652 and divide it by 4, because 4 moles makes that much, so we need to figure out how much just 1 mole makes. When we do that, we find that we are going to release 413 kilojoules of energy. Now the next one says how much energy is released when 0.067 moles of iron, react. So again, we know that either 4 moles is going to produce 1,652 kilojoules, so we could use that. Or we could actually use the information that we calculated in B. We could use that 1 mole is going to produce 413 kilojoules. So basically we turn it into a conversion factor. We know that relationship. We're going to take the amount we have, 0.067 moles of iron, and we're going to multiply it by either one of those relationships. Either the relationship that 1 mole is 413 or 4 moles is 1,652. No matter which way you do it, you're still going to get the same answer. 27.67 kilojoules of energy is going to be released. Okay? Then finally, very similar for this one as what we've done before. Again, because the balanced reaction only tells us the number of moles and how much energy, we need to convert 12 grams to moles first. So we look on the periodic table, we find the molar mass of iron, is 55.8 grams. So that means that if we've got 12 grams of iron, we have 0.22 moles of iron. Again, we can either use our relationship that we figured out from letter B, that 1 mole is going to produce 413 kilojoules, or we could use the relationship from the balanced equation, 4 moles is going to produce 1,652 kilojoules of energy. No matter what, we want to figure out how much kilojoules only 0.22 moles is going to make. So I'm going to show you the setup, and either way we can use the 1 mole produces 413 or 4 moles produces 1,652. No matter what, you're still going to get 88.8 kilojoules of energy. Okay, so finishing up, delta H is our enthalpy. And remember that enthalpy is basically our change in heat per mole. So our unit is going to be kilojoules per mole. So here's where things are a little bit different. Q, we calculate by taking mass times the specific heat times our change in temperature. Our enthalpy is going to be our change in heat per mole. So if Q is negative, then we have an exothermic reaction and energy is released, and that means that delta H will be a negative as well. And if we have a positive Q, then that means energy is going in and energy is absorbed. That means that delta H will be positive. So our energy has to be a product in an exothermic reaction, and in an endothermic reaction, the enthalpy, our energy, is a reactant. So in these problems, you can see that we don't have an actual chemical reaction. So how do we find out the enthalpy? Well, here's what we have to remember. We have to remember that delta H is going to be in kilojoules per mole. So when we think about this, it tells us our kilojoules and it tells us our moles. So we actually want to find delta H by taking our Q and dividing it by our number of moles that we have. Now our Q here, it must, for these problems, be in kilojoules. So to solve this problem, all that we have to do is we have to take our kilojoules, which is 413.5. It does say requires, so that means going in. And we're going to divide it by our 5 moles, which means that our delta H is going to be 82.7 kilojoules per mole. And that's it. We take Q and we divide it by the moles. So if we look at number 2, we want to find the combustion of 0.677 moles is going to be producing 1340 kilojoules of heat. So again, our delta H of our reaction, we take our Q and we divide it by our moles. Our Q is in kilojoules, so we're going to take 1,340. It says it's producing, so that does tell us that this is negative. Energy is exiting. And then this is 0.677 moles. So we're going to take 1340 and we're going to divide it by 0.677. So our delta H is going to be a negative 1,980 kilojoules per mole. The next one is a little bit different because remember, delta H has to be in moles and it's going to be Q per moles. So we've got our energy, we have our Q. What we don't have for this next problem is our moles. So that means we're going to have to do some stoichiometry. So we're going to have to convert our 23.2 grams, and we're going to need to convert that into moles. So 23.2 grams of sodium iodide, we know that we can look at and find the molar mass of it. So 1 mole of sodium iodide is 149.88 grams. We get that on the periodic table. We look at the mass of sodium, we add it to the mass of iodine. So that tells us that our number of moles is 0.155 moles of the material. So now we have our moles. So now the next step is to find our enthalpy of the reaction. We know that we are producing 120 kilojoules of energy, and we know that our moles is 0.155 moles. So I just put that into my calculator, and I find my enthalpy of my reaction is negative 770 kilojoules per mole. So pause the video for a second. Try to do this last one on your own. Do be careful because we do need to be in kilojoules, and this is in joules, and we need to be in moles, and this is in grams. So first thing I'm going to do is I'm going to convert my 14.99 grams of sodium hydroxide. I know that 1 mole of sodium hydroxide has a molar mass of about 40 grams. I use my periodic table to find that, and I find that I have 0.375 moles. Now the other piece of information, my joules, in order to calculate my delta H, I need to have my energy in kilojoules, and I'm going to divide that by my moles. So I'm going to take 18,300. I'm going to divide it by 1,000. That means I have 18.3 kilojoules of energy. So to calculate my delta H, I'm going to take 18.3, and it does say that this is energy being produced, so that means it's exiting, and I'm going to divide it by my number of moles, 0.373 moles, and I'm going to find that my delta H is 48.8 kilojoules per mole are being released.